Thank you. All right, guys, so remember, this is all still mostly revision from Year 10 stuff. How to express vectors, direction, we're going to look at using conventional bearings. We're going to be playing with Pythagoras quite a lot because that's where everyone is at in maths. But please recall, we can look at the sine and the cosine rule. There are examples where we're combining two vectors that might not be at right angles to each other. Okay? In that case, we can use Pythagoras. Now, there is a component method, and I don't know if I've got space for the component method.
You can use component methods now.
Yes, and I'm just looking for if I made... Could we please find some room... Let's just go to the bottom of page 7, please. Actually, no. Wait. Let's start the lesson, shall we? Yeah. All right, so page 8, let's have a look. This is a skill that you are expected to be able to do very easily. Now, we will need to split our vectors up into components. Often it will be horizontal and vertical. I prefer to use X and Y, okay? So if you're given a vector magnitude and an angle, then obviously in this diagram, we've got U sine theta as the vertical, and we've got U cos theta as the horizontal. Bergsma. Spencer. Last chance. Please stop talking. Just be careful if you are given the other angle. Sometimes we like to trick you by giving you the angle to the vertical. And so if you were given phi here, obviously everything changes. The y would become cosine and the x would become sine. So just tread carefully there. What we sometimes need to do is split our vector apart because only one component might be changing. Maybe gravity is causing the y component to change. Then we can always recombine. So just remember, we can resolve... Oh, what's wrong with your pen? You didn't... Could somebody lend me their pen that might work, please?
Thank you, sir.
Cooper? Thank you.
That's a lot of staples. Yeah, how much does that cost to replace?
Guys, we're going, yeah? We can resolve using Pythag and tan. So let's look down here. We'll look at an example. I'm going to save some space on this page because this is a really easy kind of question. So a dog's lead makes an angle of 30 degrees to the ground. The owner is pulling on the lead. So we're going to just draw the force like so. We are given the angle to the ground. So that's a bit ambiguous. We'll say the angle with respect. So really, by applying this force, there is a certain component acting in the horizontal, that is Fx. And then there is a certain force lifting the dog off the ground. So that would be our vertical component, Fy. Could you please just make a note? Dashed lines, all right? So if we ever need to split a vector, please, the components are dashed lines. That way you are saying that that is not a vector, that is simply the vertical component. Because if I was to draw 3 bolded lines, then that's saying that there are 3 different force vectors acting. And you'd end up getting double the magnitude of your hypotenuse because you'd combine them. So, the force lifting off the ground, that would be Fy, that would be F sine 30. So that would be 218 sine of 30. And I think Josh and Hugo were discussing this just then.
Yeah.
What do you get?
109 is sine 37.
Okay, 109 newtons upwards. All right, so don't forget, you are asking for a force. It is asking for a direction. And then the force pulling it along, pulling on the lead. What is the force pulling it along? I'm just trying to identify what direction it might be acting in. Gives us, what was it?
188.
Oh, it's written down there. Let's go 189 newtons left as per the diagram. Okay? All right, now, let's just quickly assign this section here for the component method. Component method. This is useful if you have more than 3 vectors. Or more than 3? More than 2. If you have more than 2 vectors. If you had 2 vectors at any angle, you could just combine them. You would make a scalene triangle. You would use the sine and cosine. But if you've got 3, using the tail to top method, Matthew Gamble, close it please. If you have 3 vectors and you combine them using the tail to top, then the resultant is going to be a 4th vector. You have made a sort of quadrilateral, and you can't use the sine and cosine because you're no longer dealing with a triangle. So in that example, the component method is going to be suitable. But first, we need to assign your convention at all times. All right. So let's give a few. Let's just go north, south, east, west. So I'm going to do an example here where we're going to have displacement 1 is 20 meters north, 30 degrees east. I'm just making these up. I'm running off the script. S2 is 100 meters west only for now. S3 is 40 meters south, 30 degrees east. Okay? Now here, graphical method's not going to help us. We could get our ruler out and some graph paper and a protractor and we could try and draw scale vectors, but that is inaccurate. All right? We could try and draw them on our quadrant. What have we got? We've got like one of them, and then we've got one of them, and then we've got one of them. So if you try and draw a tail to top method, where are we going to be? We're probably going to be in that bottom left quadrant. I think that if we added all of these together, Hugo and Josh, please stop talking. I think if we use the tail to top method, 1, add 2, add 3, I think our resultant's going to be down in that quadrant. Here's what we're going to do. We're going to split them into our x components and our y components. So we'll have S1, S2, and S3. Then at the bottom, we're going to sum them together. And then we're going to recombine using Pythagoras. So here's where we need to be careful. The easiest one is S2. Let's look at S2 first. Because, for example, S2, it doesn't have a y component. Its x component is purely in the west, which I've assigned as a negative 100. So that's me splitting my vector. Now, some of you might be more familiar with I and J and K notation. Try not to use that. In year 11 and 12 ATAR physics, we don't use I, J, K, we use X, Y, and Z. Okay? So, let's go to this first one. North, 30 degrees. So really, if I want to split this up into the X, it's going to be sine. So over here, it's going to be 20 plus 20 sine 30. And then our Y component is going to be plus 20 cos 30. For S3, we're down here now, 30 degrees. And so now our S3 in the X component, it's going to be plus 40. And we want the sine 30. And then the adjacent would be cosine, so it's now negative 40 cosine 30. It's negative because we assigned that north is positive, south must be negative. So the y component of my S3 vector is acting in the negative. Okay? Now, you could do all of the x components in your calculator. Could everyone do that? Let's get your that crow is less annoying than the mumbling and murmuring that I hear from the back of the room.
Admission control.
You can close the door, Hugo, yes. Everyone, get their calculators out. You can sum, let's sum the x's together. So, I'm just going to use brackets to split my 3. So I'm going to go 20 sine 30, bracket, bracket, take 100, plus bracket 40 sine 30. Negative 70. Okay, that kind of agrees with me that I reckon that the resultant of those 3 vectors is going to be in the west quadrant. So we get negative 70. That's a nice round number. How convenient. Then let's find the y. And again, I reckon we're going to be down here in the negative. So I'm reckoning the y component, the sum of the y's, will be negative as well. So 20 cos 30 minus 40 cos 30, negative 17.3. So now if I wish to recombine my vector, we're going to go across by 70, down by 17.3. Okay, again, Pythagoras and arctan to find magnitude and direction. So we could say that the sum of the displacement vectors, we have done this in the previous lesson, so I'm just going to do this without writing it down. It's going to be square root of 70 squared plus 17.3 squared gives 72.1. And then the angle, I'm going to go the arctan opposite, which is 17.3 divided by adjacent, which is 70. We're going to get 13.9 degrees. So that's going to be west 13.9 degrees south. Oop. Now, this is the best way to do an addition of 3 or more vectors. Okay? And I believe there was a question in maybe 2 years ago or 3 years ago, the physics motion and force test had this kind of question. Maybe it's time to throw it into this year's test because it hasn't been there for a couple of years. Okay, so that is a method for more than 2 vector additions. Okay, so split them apart, combine the x's, combine the y's, then recombine using Pythagoras and...
Well, what was your answer for the direction, sir?
Well, west 13.9 degrees south. Cool. All right. Vector subtraction. Sometimes we need to look at not adding vectors, but looking at the difference between 2. And you might be familiar with the term delta. Delta means the change in. It means final minus initial. Delta V, you're going to be looking at in great detail. Delta S, not so much, but you can get change in momentum, change in force, change in mass. Well, that's a scalar. Let's go back to vectors. Delta V can be written as V final minus V initial. It can also be written as V take U, which can also be written as, and here's the kicker, V add negative U. So we can add the negative. Okay? So, have a look at this question. A car moving at 15 suddenly brakes, slows down to 5. So this is V, and this is U. Now here's what we're going to do. We're going to say, all right, V equals positive 15. U equals positive 5. It's still traveling in the same direction, but I'm now going to go negative U equals negative 5. Okay? This is the correct maths. The change in velocity is 10 meters backwards, but you can't just write 10 meters backwards. You've got to show some mathematics. You've got to show some logic. So we'll say our delta V is V take U Wait a second. I've stuffed this up. Sorry. My bad. V is, the final is plus 5. The initial was plus 15. Sorry, so the negative U is going to be negative 15. My bad. I'll give you some time to get your whiteout out and make that correction. V is now plus 5 plus negative 15 equals negative 10. And remember, we never express direction with plus or minus. We always convert it back 10 meters per second backwards. Because we were given the convention that forwards is positive. So you were asked to use the convention forwards equals positive. Okay? All right. Now let's look at this one. A ball falling onto the ground. Initial is negative 10. Why is that? Maybe it's because I assigned that down is negative, so up is positive. There we go. Let's force you to use the convention. Strikes the ground and then rebounds. V equals plus 5. Okay. So look at that, negative u is now positive 10. So delta v equals v, add negative u. Okay. And that makes sense that you had to change your downwards vector by plus 15 to turn it into an upwards vector. Another way to look at this equation is to say that your final is going to be your initial plus any change that has occurred. Okay, so have a look. Is my final, is 5 equal to negative 10 plus 15? Yes, if we took a negative 10 and we added 15, the result would be a 5 meters per second upwards vector. Okay? Let's get a little bit trickier. We can still use a graphical method. So we just looked at two examples that were in the same plane, up, down, and backwards, forwards. Now let's look at X and Y components. Now, again, I've just taken a screenshot of this just to save time. Could we all just stare lovingly at this billiard ball? It's coming in at 3 meters per second at an angle of 45 degrees to the bumper. So this might be the cushion of your pool table. Okay, that's a little bit harsh. Let's go down a bit. And then it actually recoils, collides elastically. There is no loss in energy. And there's no backwards retarding frictional force opposing its forward motion. This is an unrealistic scenario. This is a perfectly elastic collision. Okay? In which case, my negative u, if I draw my initial velocity vector in that direction, then negative u, I can just draw it in the complete opposite direction. Okay? Then I'm going to add that to v. So if you look at my diagram down here, all right? So there's my v, take u, then the resultant is delta v. Okay? Now everything came out quite nicely here because I picked the angle 45, that makes this interior angle 90. Oh look, that's Pythagoras. So it actually just became a nice easy right angle triangle. The change in velocity is the magnitude of the Pythagoras. And then the angle came out as 45. Now that's this angle here. That was the angle with respect to v. We don't want it with respect to v, but look what we had. We had 45 and then 45. So it actually makes that the change in velocity was directly outwards from the cushion. Which generally makes sense because in order for the ball to change its velocity by that, there needs to be a force acting in that direction to produce an acceleration in that direction, which produces a change in velocity in that direction. And it would make sense that if a ball strikes a wall, the wall really only can push outwards. That's one of the rules of the normal force of a surface, is it can only really push at 90 degrees to its surface. And that's what we're seeing here. the cushion pushed the ball at 90 degrees to the surface to produce this change. Okay? Activity. All right, I want you guys to do this now. Let's figure out what the change in velocity of a car. Let's not worry about how long it takes. Let's not worry about the shape of the corner or the road. Let's just say we started off travelling that way, and then we turned right, and then we travelled north. So, could you please draw your car, draw your final and initials, draw your negative U, add V to negative U. Yes, Farad?
So why was it at 90 degrees to the cushion when the answer was 45?
Well, no, so when we solve for that angle, you'll notice that that's the angle between delta V and V.
Okay.
You don't ever want to express delta V with respect to another vector. We want it with respect to north, south, east, west, up, down, left, or right.
Okay.
And so to get it to the cushion, we used that the cushion is a straight, and we had the supplementary angles 45, 45, and the angle we wanted was 90. Okay? So obviously, guys, with this graph, this is a graphical method. You draw a diagram. It will always help you to figure out the answer. Well, I'm just going to cheat and use the values given. Okay. Hands up who's finished this question. Nice, 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 nice. One other way to look at this is we were currently travelling west, and afterwards we had no west component. So to remove this west component, then my change in velocity must have a backwards west. There's the backwards west component. And then, at the start, we had no north or south component, and then at the end we did have a north component. And so my delta V must have that north component. And there it is there. Okay? One other way to look at this is if I said, here's my U, if I added my delta V to U, the delta V, sorry. If I said, let's just add my change to my initial, then we would be left with that. Okay? And normally I color code them, so how about we color code? Let's go U plus delta V. My resultant of that would be that. Okay, so that's how we have to change U. If I want to change that vector to become that vector, then my change must be bending my initial vector back to that point. Yes?
Why on the far right-hand diagram?
Yep.
Wouldn't you put it, because you're traveling west first and then changing to north?
Yep.
Wouldn't you put the V above the negative U?
Would you put the V above the negative U?
Which would change the angle.
Yeah.
The position of the angle.
This angle here?
Yeah, no,
Well-
as in, yeah, it'd be the opposite angle.
That one.
Yeah,
That one.
and you're travelling in the other direction.
You could express this as east 60 something degrees north. It's just happened. We remember we don't want to express this angle with respect to V, but it just happened that V was north. And so if I wanted to express that red vector with respect to north, it is that angle. So I don't have to do any adding or subtracting of my directions. We had the direction with respect to north. Just like we had this angle here would be the direction with respect to east. All right? So it just happened to be the car was north, south, east, west directed. Let's look at this one. Now, this is an extension question. Oh, hang on. Why is it that says extension, but this one's not? Oh no, look, you've got north and east. This is okay. Here we go. This is easy. This is easy. Here's my billiard ball. It's traveling north. And then somehow it hits a cushion and it bounces at east. So I reckon the cushion might be like that. And so when it hits, it then goes doing like that. Okay? In which case, there we go. Does that help? Okay? I'm just going to bring this. Yes, is that good? East and so now my delta V. So I've got my V.
Could there possibly be the same the answers or wrong?
I don't know. What's the square root of 13?
The direction.
I don't know. What's the arctan of 2/3?
Yeah, it's 33.7. Unless this calculator.
Not that I don't believe you, but I just want to check.
Yeah, there's 3.
33.7? All right. Thank you. Okay, magnitude. That's not 14, it's 13. Now, what have we got? That angle is small, so it's directed east, and then it's pushed 33 points, or rotated that direction south. All right. Not to what's the phrase, target you out, but are there any APS students in this room? If you could kindly raise. Okay. I'd like us all to try this extension question. It will involve a what's the triangle where none of the side lengths are scaling? No.
Yeah,
One of the-
they're not.
No, yeah, it'll be a scalene triangle. Now, guys, in this scenario, you have been given 2 side lengths, and you have been given 2 outside angles. You have to try and figure out an inside angle for your triangle. Okay? So you've been given the angles with respect to north, south, east, west. Then you should be able to find an internal angle. Once you've got that internal angle, you can go sine and cosine rule to find your answer. Okay? I will give you 2 or 3 minute head start, and then I'll start setting the question. Yes. No. What you've just calculated is V plus U.
So,
We don't want V plus U. We want V take U. So take U from V. And negative U. So negative U is 2 meters south. You're going to add 2 meters south to your line.
So B plus negative
We add negative U. Yes. So that's the key thing. You've got to add the opposite of U. If you add U to V, then you're just getting V plus U. That doesn't give us anything useful. Unless the average, if you want the average, that's V plus U on 2. So I mean, you could add V and U together and then divide your resultant magnitude by 2. That would give you the average speed. We don't really worry about the average speed. We want to know what the change is. That's fine. Come and see me.
Well, the thing is, that's not done because B plus another change
You draw a different triangle. So you need to draw a different triangle. Yeah, so if you draw the other triangle, then your side legs are gonna flip. Okay? Alright. Wait, is this the 3.5 at 44? Yes. Okay, let's see what we got here. We want to go V. Here we go. Add negative U. All right. Oh, I think this one is easy. Did anyone manage to get the internal angle? What if I drew two parallel lines, dashed parallel lines? Could I use my co-interior or my alternate angle rule to figure out the angle below the dashed line inside the triangle?
Should that angle be 46?
No, that was 44 west, 44 south.
which one's that?
Basically, it was initially travelling west, 44 south. So no, it's 44. I'm hoping. There's no 46 anywhere. Come on, guys. How can we find that internal angle? Would you like me to show you?
60 degrees on opposite.
Then that's 60. And if that's 44 and that's 60, then we've got the total internal angle as 104 degrees. Okay? So now, how much room do I have? I could probably zoom this out a little bit. Oh, that's not. Okay. So now you use the cosine rule to find your magnitude, and then you might want to use the sine rule to find phi. Okay? But remember what I said, this is not in the course. If you can do this question, then you're pretty much 100% on vector addition and subtraction. Okay? So what do we got? The square root of a squared plus b squared minus, what is it, 2ab?
Yeah. 2AB cos C.
Cos c, and look at that, we've got cos c as that. And I'm hoping that your calculator spits out 5.28.
It does.
And now let's find phi. So sine phi on 3.5 equals sine 104 on 5.28 times both sides by 3.5.
0.643. And then minus sine of the answer is 40 degrees.
Is it? Do,
Yeah,
30,
phi is 40.
do we get 36 degrees or no?
I got
40?
40. Yeah.
Okay.
40.02 or 3. So.
All right. Now,
Wouldn't it be simpler to use component for this question?
you could, but since there's two, I would go sine and cosine. Sam Duncan, what's wrong?
Hit the wall at 3.5 meters per second. On your diagram, you said it was 3.2, and the other was 3.5.
That's not the.
Oh, hang on. So that's not right.
On your other one,
No, that's
3.5.
It's going the opposite way. So
This is V, and that's negative
yeah,
U.
actual velocity. So it hits it like that. You got that, right? That's 3.5 hitting it there. This is saying it bounces off there. It goes down.
That's V take U.
Yeah.
Can someone confirm the angle is 40 degrees? All right. Now, have a look here. Guys, we just solved that internal angle is 40 degrees. What just happened? I didn't want them to do that.
It's 100 degrees in total. So, and then because
And so,
north is 90, so you take away 100, take 90, gives you 10.
yep, absolutely.
Cool.
Have a look what we've got. We've got 100 degrees total sweep. Okay? But we might want to express this red vector with respect to north. And so then I can say that, well, 100 degrees sweep from the east vector around, then this is going to be 10 degrees. And so that agrees with our answer. It's been swept 100 degrees from the east direction, and so that's north 10 degrees east. So your final change in velocity is oh, that should say west. No, sorry. I said east before when I should have said west. Why are you packing up?
No, I'm going out.
Okay.
Sleep.
All right. I'm pretty sure that's me done talking for now. I can't give you your tests back. Yeah?